China just engineered a silkworm that produces a material stronger than steel. These modified silkworms spin a fiber 6 times stronger than Kevlar, the same material used in bulletproof vests. To put that in perspective, a strand the width of a pencil could hold the weight of a fully loaded school bus. You heard that right. A thread thinner than anything you've ever held, strong enough to stop a vehicle in its tracks. What scientists just pulled off in a Chinese lab is the kind of breakthrough that quietly changes everything. And to understand how they did it, you have to go back 5,000 years to where this story actually begins. The ancient thread. Imagine you are standing in ancient China, not in a city, not near a palace. You are standing in a garden underneath a white mulberry tree, watching something so small you almost miss it. A caterpillar no longer than your thumb is doing something that would take humanity thousands of years to fully appreciate. It is spinning. Not just spinning randomly. It is producing a single, continuous thread, wrapping itself inside a cocoon of its own making. And that thread, that impossibly thin filament, is silk. One of the most remarkable natural materials ever produced on this planet. For over 5,000 years, silk was treated like a form of currency. Emperors hoarded the secret of its production. The punishment for revealing how silk was made to an outsider was death. Entire trade routes spanning thousands of miles of brutal terrain were built just to move this material from east to west. The Silk Road wasn't named after a person or a place. It was named after a thread. And here is what made silk worth all of that. Worth the secrecy. Worth the wars. Worth the thousands of miles of dangerous roads. It was not just beautiful. It was strong. Remarkably strong for something so light. A natural silk thread, pound for pound, is tougher than most metals. It resists tearing. It absorbs energy. It does things no one fully understood for centuries. But natural silk, as extraordinary as it is, has a ceiling. There is only so much strength a silkworm can pack into a thread on its own. And for a very long time, scientists accepted that ceiling as a hard limit. But the ceiling was never the problem. The problem was that no one had thought to look at what was spinning silk in nature and ask a different question. Not, how do we use what the silkworm already makes? But what if we changed what the silkworm makes entirely? That question would take centuries to even become possible to ask. And when it finally was, the answer would come from one of the most unlikely creatures on Earth. But before we get there, you need to understand something that scientists spent decades chasing and failing to catch. The impossible thread. Picture yourself in a forest just after sunrise. The light is cutting through the trees at a low angle, and you walk into something you didn't see coming. A spider web. You pull back instinctively, brushing it off your face, and in that split second of frustration, you just made contact with one of the strongest materials in the natural world. Spider silk. Specifically dragline silk, the kind a spider uses to build the frame of its web and to repel from surfaces. Scientists have known for decades that this stuff is extraordinary. A single dragline thread is, weight for weight, stronger than high-grade steel. It can stretch up to 40% of its own length before snapping. It is incredibly lightweight. It is naturally biodegradable. And it is tough in a way that almost defies explanation, absorbing impacts that would shatter harder materials outright. For decades, material scientists treated spider silk like the Holy Grail. If you could produce it at scale, if you could manufacture it the way you manufacture nylon or Kevlar, you would have a material that would rewrite entire industries overnight. Medicine, defense, aerospace, construction, all of it. So they tried. For years, they tried. But here is the problem nobody could get around. You cannot farm spiders, not at any meaningful scale. Spiders are territorial. They are cannibalistic. Put enough of them together, and they will simply eat each other. The spider that produces the most remarkable natural fiber on Earth is also biologically incapable of being farmed like a silkworm. And synthesizing spider silk artificially? Researchers spent decades attempting it, inserting spider genes into bacteria, into yeast, into goats. Yes, goats. Scientists actually engineered goats to produce spider silk proteins in their milk. The results were promising in a laboratory but practically useless at scale. The proteins were unstable. The fiber quality was inconsistent. The costs were astronomical. Every approach hit the same wall. The silk proteins themselves were not the problem. The problem was finding a biological system that could spin them, not just produce them, but actually assemble them into a real usable thread, the way nature intended. And then someone asked the question that changed everything. What if the system already existed? What if the answer was not to build something new, but to upgrade something ancient? Because there was already a creature on Earth that had been spinning silk threads for 5,000 years. One that humanity already knew how to raise, how to feed, how to farm at massive scale. One that already had the biological machinery to spin protein into fiber. The silkworm. And what happened next in a lab in Shanghai is the reason you are watching this video right now. The upgrade. You are inside a research lab at Donghua University in Shanghai. The year is recent. The equipment around you is not dramatic, no flashing lights, no science fiction theatrics. Just precise, painstaking work happening at a scale so small it cannot be seen with the naked eye. The scientists here are not trying to build a new material from scratch. They are trying to do something far more elegant. They are going to rewrite the instructions inside a silkworm at the genetic level so that when it spins its cocoon, it spins something the world has never seen before. The tool they are using is called CRISPR, Cas9. Think of it as the most precise pair of molecular scissors ever developed. With CRISPR, scientists can navigate the genome of a living organism, that entire biological instruction manual, find a specific section, cut it, and insert new information, not randomly, not approximately, exactly where they want it. What the Donghua team did was take the genes responsible for producing dragline spider silk proteins, specifically the proteins called MASP1 and MASP2, which gives spider silk its legendary strength and elasticity. And they inserted those genes into the silkworm's own silk-producing genome, not to replace what the silkworm does, to enhance it. To fuse spider silk DNA with silkworm silk DNA in a way that had never been successfully achieved before. Previous attempts at this had failed. Researchers had tried inserting spider genes into silkworms before, but the proteins never integrated properly. The silk that came out was barely stronger than normal. The spider proteins were getting lost in translation, present in the genome, but not expressing the way they needed to. The Donghua team cracked that problem by targeting the insertion point with extraordinary precision. They placed the spider silk genes inside the silkworm's own silk protein gene, essentially tricking the silkworm's biological machinery into treating the spider silk proteins as its own. Instead of fighting the new instructions, the silkworm's body embraced them. And then they waited. The engineered silkworms hatched. They grew. They fed on mulberry leaves just like any other silkworm had for 5,000 years. And when the time came, they began to spin. What came out of those cocoons was not normal silk. It was something else entirely. A hybrid fiber, part silkworm, part spider, spun by a living creature through natural biological machinery into a thread that had never existed in nature before. The results stopped the research team cold. But what those results actually showed, what the numbers actually meant, that is where this story becomes almost impossible to believe. Stronger than steel. You need to hold this number in your mind for a second. The fiber produced by these engineered silkworms tested at a toughness more than 6 times greater than Kevlar. 6 times. Kevlar, the material that stops bullets. The material woven into the vests worn by soldiers and police officers around the world. The material that is, by design, one of the toughest synthetic fibers human beings have ever manufactured. 6 times stronger than that. You heard that right. A biological thread spun by a caterpillar. 6 times tougher than the material protecting people in combat zones. But toughness is not the same as strength, and this is where the science gets even more remarkable. Steel, structural steel, the kind used in buildings and bridges, has a tensile strength of roughly 58,000 pounds per square inch. The fiber from these engineered silkworms, when measured by weight, outperforms it. Pound for pound, This thread is stronger than steel. And unlike steel, it does not snap under sudden impact. It stretches, it absorbs, it distributes force across its structure in a way that rigid materials simply cannot. Think about what that actually means. Steel is hard. When steel fails, it fails catastrophically. It cracks, it fractures, it shears. This fiber fails the way a living thing fails gradually, warning you, bending before it breaks. In engineering terms, that difference is not a footnote, it is everything. And there is one more property that separates this material from every synthetic alternative currently on the market. It is biocompatible. Your body will not reject it. It does not trigger the immune responses that synthetic materials often cause. It can exist inside a human being, inside a wound, near an organ, threaded through tissue, without causing the kind of chronic inflammation that makes most foreign materials a long-term problem. Steel cannot do that. Kevlar cannot do that. Nylon cannot do that. This material can. And it is not made in a chemical plant. It is not synthesized through an industrial process that requires fossil fuels and generates toxic byproducts. It is made by a silkworm, a living creature, spinning a thread, the same way it has always done, just with new instructions. But knowing what this material can do is only half the picture. Because when you start to look at where this material could actually be used, that is when you begin to understand just how large the implications of this breakthrough really are. What this changes. Start with the human body. Right now, when surgeons close a wound internally, they use sutures threads to hold tissue together while it heals. Most sutures are either synthetic, which the body tolerates but never fully accepts, or made from biological materials that degrade unpredictably. A suture made from this engineered silk fiber would be stronger than anything currently available. It would hold under far greater stress. And because it is biocompatible, it would integrate with the body's own healing process rather than working against it. But go further. Tendons. The tendons in your knee, your shoulder, your Achilles when they tear, the repair options are limited and the recovery is brutal. What if surgeons could replace a torn tendon with a fiber scaffold strong enough to handle the mechanical loads of a human joint, flexible enough to move naturally, and biocompatible enough to encourage new tissue growth around it? That is not a distant fantasy. That is a direct application of what this material makes possible. Now step outside the human body and into the world of defense. Body armor today is a compromise. It is heavy enough to slow soldiers down, rigid enough to restrict movement, and still not strong enough to stop every threat. Imagine armor, woven from a fiber, 6 times tougher than Kevlar, at a fraction of the weight. Armor that moves with you. Armor light enough that a soldier does not feel it is there, but strong enough to absorb impacts that current materials cannot handle. Move from defense to aerospace. Every pound of weight removed from an aircraft or spacecraft reduces fuel consumption, increases range, and improves performance. The materials used in aerospace engineering are chosen with obsessive attention to the strength-to-weight ratio. A fiber that is stronger than steel, but weighs almost nothing, is not an incremental improvement for the aerospace industry. It is a fundamental shift in what becomes possible. And then there is the environmental angle, which is perhaps the most quietly important application of all. Right now, the world produces hundreds of millions of tons of synthetic fiber every year. Nylon, polyester, Kevlar. These materials do not break down. They accumulate in landfills and oceans. They are made from petrochemicals. They are, in every sense, an environmental problem we have been deferring for decades. This silk fiber is biodegradable. It breaks down naturally. It is produced by a living organism that eats leaves. Its entire production process, from beginning to end, is biological. If this material scales, if it can be produced in quantities large enough to compete commercially, it offers something the synthetic fiber industry has never been able to offer: strength without permanence, performance without pollution. But none of that happens automatically. And the road between a laboratory breakthrough and a material that changes the world is longer, harder, and more uncertain than most people realize. Because there are problems standing between this discovery and the future it promises, and one of them is bigger than it looks. The obstacles. Here is the part that does not make the headlines. The part that the press releases tend to skip over. The engineered silkworms exist. The fiber is real. The numbers have been peer-reviewed and verified. But right now, those silkworms are producing this material in quantities measured in grams. The global fiber market operates in millions of tons. The gap between where this technology is today and where it needs to be to matter at industrial scale is not a small engineering challenge. It is one of the most difficult scale-up problems in material science, because you are not scaling a chemical reaction, you are scaling a biological organism. And biological organisms do not simply multiply on command. They have growth cycles. They have disease vulnerabilities. They require specific conditions, specific feed, specific handling. Every variable that is easy to control in a laboratory becomes exponentially harder to control at the scale of a factory. And then there is the consistency problem. Natural biological systems vary. Every silkworm is slightly different. The fiber one individual spins may differ subtly from the fiber another spins. For consumer textiles, that variability is acceptable. For a surgical suture that needs to perform identically every single time, or for an aerospace component where a single point of failure can be catastrophic, that variability is not acceptable at all. Solving it requires levels of quality control that have never been applied to a biological production process. There are regulatory questions too. These are genetically modified organisms. In most countries, the frameworks for approving, producing, and commercially deploying GMO organisms in industrial settings are complex, slow-moving, and deeply political. The science may be ready before the regulations are, and in some markets, the regulations may never catch up. The cost right now is prohibitive. A gram of this fiber produced at laboratory scale costs far more than any commercial application can justify. Bringing that cost down requires the kind of sustained, large-scale investment that only materializes when a government or a major corporation decides the potential return is worth the risk. But here is where the story takes a turn that most people are not paying attention to. Because the question of who solves these problems, who funds the scale-up, who patents the production methods, who builds the first commercial supply chain is not just a scientific question. It is a geopolitical one, and China is not waiting. China's play. Step back from the laboratory. Step back from the fiber and the silkworms and the tensile strength numbers. Look at the bigger picture, because what is happening here is not just a scientific breakthrough. It is a strategic move. China has been investing in synthetic biology and advanced materials science with a focus and a scale that most Western countries have not matched. The government has identified biotechnology as a core pillar of national competitiveness, not as an academic pursuit, but as an economic and military priority. Funding flows into research institutions. Talent is recruited aggressively. The pipeline from university laboratory to commercial application is treated as a national infrastructure problem, not just a market opportunity. Silkworm cultivation is already a deeply embedded industry in China. There are regions of the country where silk production has been the economic backbone for generations. The infrastructure, the farms, the processing facilities, the expertise already exists. Transitioning that infrastructure to produce engineered silk is not starting from scratch. It is upgrading something that is already there. And here is the part that should make the rest of the world pay attention. Whoever controls the production of advanced materials controls the industries that depend on them. Defense contractors need material supply chains. Aerospace manufacturers need material supply chains. Medical device companies need material supply chains. If China is first to scale engineered silkworm fiber to industrial production, if Chinese companies hold the key patents and run the key facilities, then every country and every company that wants to use this material will need to come to them. That is not a hypothetical leverage play. That is how advanced materials have worked throughout history. The country that controls the material controls the technology. The country that controls the technology shapes the century. China is not doing this by accident, and the rest of the world is only beginning to realize what is at stake. But even as that geopolitical race accelerates, there is something larger happening here. Something that goes beyond China, beyond steel, beyond body armor and surgical sutures. Something that this breakthrough is a signal of a shift in how humanity itself approaches the problem of building things. And when you see it clearly, it changes how you think about everything that is coming next. The silkworm and the future. You have been building things the same way for most of human history. You dig materials out of the ground. You heat them, refine them, compress them, cut them. You force raw matter into the shapes you need through processes that require enormous amounts of energy and generate enormous amounts of waste. Steel, aluminum, plastic, concrete. The entire built world around you is the product of that approach. Extraction, transformation, construction. But nature never worked that way. Nature builds by growing. Every remarkable material in the biological world, bone, shell, wood, silk, is assembled from the bottom up, protein by protein, molecule by molecule, at room temperature, using nothing but sunlight and chemistry. No furnaces, no refineries, no toxic byproducts. Just life, doing what life does, and producing materials that, in many cases, outperform anything human engineers have managed to manufacture. Biomimicry, the practice of learning from biological systems to solve engineering problems, has been gaining ground for decades. Scientists have studied the way gecko feet grip surfaces to develop new adhesives. They have studied lotus leaves to create water-repellent coatings. They have studied the structure of bone to design stronger, lighter alloys. Nature keeps proving itself to be a better engineer than we are. But what the Donghua team did with these silkworms is something beyond biomimicry. They did not just study nature and copy it, they edited nature. They reached into the genetic code of a living organism and upgraded it, combining the silk-producing infrastructure that silkworms have refined over millions of years of evolution with the protein blueprint that spiders developed for their own purposes. They use life itself as the manufacturing platform. And that distinction matters enormously. Because once you accept that living organisms can be programmed to produce advanced materials, once you have the tools to do it and the proof that it works, the silkworm is just the beginning. Imagine bacteria engineered to produce structural fibers stronger than carbon fiber. Imagine fungi that grow into insulation panels with thermal properties no synthetic foam can match. Imagine trees modified to produce timber with the load-bearing capacity of steel beams. These are not idle fantasies. They are the logical extensions of exactly what just happened in that lab in Shanghai.
The silkworm that has been spinning for 5,000 years just became a proof of concept for a new kind of manufacturing, one that does not dig, burn, or pollute, one that grows, one that lives.
You are watching the first chapter of that story being written. And the thread at the center of it, lighter than a feather, stronger than steel, spun by a caterpillar on a diet of mulberry leaves, is the most remarkable material on Earth. Not because of what it is, because of what it tells us is possible.